used for live migrations. Okay. DL bar operations, which are dynamic partitioning operations, also rely on CPU hotplug to adjust the size of VM in a virtualized environment at runtime. So we hypervisors, in platforms which support dynamic adjusting size of the VMs dynamically, there we make use of hotplug infra to do that. Okay, next slide, please. Okay, so I just wanted to give about like how it is implemented. So back when we were using CPU hotplug for hardware failure, to support hardwares that were failing and let the kernel run and remove them. At that point, even at that time, we were using the way it was implemented was we used notification-based mechanisms where subsystems that needed to be notified that a CPU is being hotplugged, which is either being added or removed. So those subsystems would register a callback with the CPU hotplug infra, and then at the point when a CPU hotplug operation is started, those callbacks will be invoked. The third point where I talk about the implications of sections. So we'll come back to this third point. And back then, as I understand, there was no so as number of subsystems grew, there was no formal definition of some dependencies which callbacks were supposed to be executed in what order. Can we go to next slide? Okay, so this is how Linux CPU hotplug facility works in Linux kernel right now. So efforts were made to bring some sort of formalization where the current implementation we have a state machine which tracks the state of a CPU which is being hotplugged, and this state machine is has a linear state space where each state. So we start from the CPU offline as the initial state, and CPU hotplug online will be the last state of that state machine. And the subsystems that wants to be notified, they will allocate or set up a state either statically or dynamically. And when a hotplug operation has started, the state machine will move from one state to another based on how if the callbacks were successfully executed. As you can see, so when a CPU is coming online, let's consider that. The entire states, there can be different points in time where a subsystem wants to be notified. So for example, this state machine is divided into 3 phases, where first phase is prepare section, which is a set of states, and then we have starting section and online section. As a part of so callbacks which are part of prepare sections are executed by some other CPU, the CPU which is supposed to be hotplug. So in case of online operation, the CPU that is coming up is not yet started. So the prepare section callbacks are invoked on a different CPU. Starting section and online section, the states are callbacks are executed on the CPU which is being hotplugged. And each state, so when a subsystem is setting up a state, it can supply 2 callbacks. One is startup and tear down, and the CPU hotplug infra will take care of invoking them as part of either online or offline, either online or offline. Either we are bringing up the CPU or we are offlining a CPU. Okay, as a part, so CPU, I wanted to highlight the CPU hotplug bringing up CPU. So this is the state which is the last state in the prepare section, which means this is the last state. My control CPU, which is the CPU, it is the CPU which is given the task to online some other online or offline the other CPU. So in case of a bring up operation, CPU hotplug bring up CPU is the state which is the last callback will be executed by the control CPU, and after that we are going to kick. After that state, the secondary CPU will come up and start executing instructions. Yeah. So next slide, please. So the thing is, if you have any doubts, you can ask right away. Yeah.
How does this handle initial CPU configuration like pin mounting or something when we hotplug the new CPU?
So pin, what do you mean by pin? Pin mounting means what?
So in the source sequence will be allotted to different buses and devices. So if the CPU is going to come online later, we will be using a device we have to specify. So do we have to do it, or is this only about exits?
No. So this CPU hot plug here deals with adding and removing from running kernel's perspective. So it's not if your OEM supports physically hot plugging, that is a separate thing. Here what we do is this is Linux kernel infra, where once we remove the CPU, no work will be scheduled there, no interrupts will come there, no timers will be there. So from operating system's perspective, this CPU is not there anymore. So no work will be even though the CPU is still there. I mean, physically, example. If you are onlining, so once the CPU is fully online, kernel will start making use of that CPU to schedule work there. Processes okay. So intentionally not added any code, but there should be some mechanics.
When you say the CPU is fully online, right? Yes. What do you mean? Like, who does the initialization of the CPU?
Who does the initialization? So can we go back? So consider a situation where you have booted your on your Android system, I suppose, and your Android system currently has 8 CPUs. And when you are booting your Linux kernel, you can specify through a command line option that I want to boot with just 6 CPUs, even though there are 8 CPUs on your system. And later on, you want to bring those 2 CPUs online. So what will happen is you will initiate from the Linux kernel that I want to online these last 2 CPUs. And let's look at what will happen for one particular CPU case. So initially, that CPU will be marked offline as far from the kernel's perspective. And this task of onlining this new CPU will be handled by some other CPU. So that is the CPU which is control CPU, where and as a part of onlining this new CPU, which means there are multiple subsystems in my operating system that needs to be notified because they are maintaining some state for that CPU. For example, scheduler is one of the subsystems that needs to be notified, because if scheduler does not know that there is a 7th CPU, it will not even schedule processes there. So that is one example. There can be other examples. For example, your ftrace. So if you are using ftrace to trace all the kernel functions that have been executed on that CPU, there needs to be some sort of a buffer that needs to be maintained. And these subsystems will usually, what they will do is they will ask the CPU hotplug, they will register a state. So ftrace will register a state somewhere along this state machine, and it will say that invoke this callback for me when this CPU is coming online. And once that callback is invoked, depending upon where that state is present, if it is present in the prepare section, then those callbacks will be invoked by the CPU which is already online. Okay, and what will happen is, so the thing is, when you boot your system, very early there is no concept of processor at that point in time, and there is no concept of a proper memory allocator, right? So for example, in starting section, the callbacks that are invoked, they are invoked. So at that point in time, there are no K threads and all have been created for that CPU. So usually all the callbacks that are executed in starting sections are invoked in an interrupt disable. So that gives this dependency that my callbacks cannot sleep. So if interrupts are disabled, my callbacks cannot sleep. So I cannot create K threads and all in the starting section. So that's how this this state machine was divided. I mean, people who worked on it, they thought about different scenarios. Like a subsystem might want to create K threads, but if that subsystem wants to create a K thread, that subsystem cannot register the callback in starting section. But depending upon the requirements, some subsystem wants to be notified very early, even before my CPU has started executing instructions. So in that case, they will register their callbacks into there to allocate memory, so that when that CPU comes in, it will you have all these per CPU memory created and whatnot actually. Okay, so what happens inside that callbacks that subsystems have registered is like a black box for CPU hotplug, because the job of CPU hotplug is, you provide me a set of callbacks that needs to be executed in some order, and it will just go ahead and execute them. Okay, so there needs to be some mechanism where we.
What is the latency between offline to online?
Yeah, we will talk about it. So the thing is, currently the way it is, yeah, I mean, depending upon how many CPUs you want to hotplug, at a time we can hotplug one CPU at a time. So there can only be one CPU hotplug operation running in Linux kernel at any point in time. Even though if you try to hotplug many CPU in one go, there is a kernel. It's like a top level hotplug law, which will synchronize all those multiple hotplug operations. So if you want to offline just one CPU, depending upon how much large a system is, the time taken to perform one CPU hotplug operation will vary. So if you are trying to hotplug a CPU in a 2000 CPU system, the time taken to do that will be different than in case of your, let's suppose, in your Android. On your or any small system or on your laptop.
Does it depend on the
okay, so we are just talking SoC vendor. So once you okay, so if we go back to the last slide again. So up till now we were discussing an online operation. Let's talk about what happens when we are doing an offline operation. So the thing is, the state machine will start somewhere here, and it will start executing callbacks one by one. And these online section and starting section. In case of online section, what happens is those callbacks are being executed by the hotplug CPU, the CPU which you are trying to offline. And all these callbacks are subsystem specific. They are Linux kernel specific. So scheduler will be notified that the CPU is going away, such that it does not wake new processes or schedule new processes there. But what about processes that were already scheduled, ready to run? They were part of the run queue. So those CPUs, those processes needs to be migrated away from that CPU, so that because at some point in time the CPU is going to stop executing instructions. Right. So that is going to happen as in the last step of the starting section, moving from right to left. So when you say, is it SoC specific? I think it is not. It would not. I mean, at some level, it will be after some point. For example, once that CPU has stopped executing instruction, and you want to bring it back. So for that CPU to come out of firmware, that time will be from platform specific, I think. Yeah. So I mean, it's just everything is happening in Linux kernel, so it is not. Some parts of it are architecture specific. For example, what instructions, what is the last instruction that CPU executed to put itself in low power, or to completely stop itself from executing instruction.
So with this, we can do echo 0 as root also CPU to take it down.
Yes.
The same thing is happening.
Can you repeat? You said through a sysfs file, we can do an echo 0 to that file, and it will shut itself down. Yes.
So is it under the hood? Is it the same?
Yeah. Yeah. So there are some sysfs. So in sys devices system CPU 0, there will be a file which you can write an echo 0 to it, and that that interaction will invoke CPU hot plug under the hood. Will start the start. It will set off the start state machine.
But I believe CPU 0, we cannot take offline.
So in x86 you cannot offline CPU 0, but I think there are patches which you can enable some config which will support offlining CPU 0, because I think in x86 CPU 0 is special. But on power platform you can offline any CPU you want. There is no dependency as such. So can we? Okay, so there has to be some way to track what is the current state of the CPU that is being hot plugged. So we have some data structures, I mean, which tracks what is the current state and what is the target that we want to reach for that CPU, and whether it is an online operation or offline. That is being tracked using this Boolean variable. Yeah, so the implications of those sections. So remember I was talking about that there are some implications of the section. Those implications are this: that if a subsystem wants to be notified, where it wants to be notified, in which section. So in prepare section, all the callbacks are invoked on a control CPU. In the starting section, the callbacks are invoked on a hot plugged CPU, but with interrupts are disabled there. And in case of online section, all the callbacks are executed under the context of a per CPU hot plug thread, and with interrupts are enabled. So once the CPU has reached the online section, has started executing callbacks in the starting online section, if other threads are scheduled on that CPU, they will context switch, and that CPU will execute. Yeah, so the operating system can start scheduling jobs there.
So, yes. So the scheduling subsystem, what does it do? Where are the callbacks registered?
Where are the callbacks registered?
Which of?
Okay, so for scheduling, scheduling actually, so subsystems can register more than one callbacks actually. So for example, RCU, I'll give example of RCU and then I'll come back to scheduler. So RCU subsystem has registered 3 callbacks: one in prepare section, one for CPU dying, and then one for online. So, and in case of scheduler, what happens is scheduler also has registered more callbacks, but the last callback of online section is also a scheduler callback. So once this before becoming online, scheduler is notified one last time that this CPU has completely become online. So and now you can schedule tasks there. Yeah. So if I am doing an offline operation, so scheduler is the first subsystem that gets to be notified that this CPU is going away. So as part of that, it will as an example, as part of that callback, what the first thing that scheduler will do is mark that CPU offline or inactive. So offline will the CPU gets marked offline is at the end of the third phase. Online is at the start of the online section. Yes. But it gets marked inactive such that no new wake-ups are scheduled there, or the tasks that are already being scheduled there, they should get moved out.
So alloc and dealloc, or even the non-queues associated with that.
We can, but I don't think so. Right now, we don't do so. Right now, we create run queue data structures for all the possible CPUs that can be made online anytime in future. So yeah, I mean it is. So right now it's there. I mean those structures are allocated. Usually, what I have seen is for this RQ structure, I think it is statically allocated, but I will have to check. So it is, but I am sure of that it is allocated for all the possible CPUs. So even if the CPU is offline, architecture will still be there. For example, some advanced. So okay, so for example, there are per CPU k threads. If a CPU is going offline, one would argue that so earlier we used to deallocate the task struct itself, but now there has been in the k thread subsystem itself allows you to park that k thread. So you don't need to deallocate the task struct at the time of hot plug. You can just park it such that it never gets to run. And then once that CPU is online, we can unpark the k thread. Can we move to next slide? One before. Yeah. Okay, so let's talk about what is the current, what has, what are, I mean, I say it as issues with CPU hot plug. But the thing is, as new subsystems were created, so those subsystems have registered. So currently we have around 237 states in the state machine, although not all of them are active in a live kernel. And the number of states that are active can depend on architecture to architecture. So for example, on my x86 laptop, there are 91 states, and on a PowerPC system, there are 71. So some of these state callbacks are architecture specific. They are also, so for example, a driver might want to be notified that the CPU is coming online or going offline, so it might also register. So depending upon whether that driver is present in the system, that state will be active or inactive. Okay. Okay. So one issue that we kind of faced was we were trying to do bulk CPU hot plug operation. So we wanted to offline a majority of CPUs in the system. But because of the nature that there can only be one CPU hot plug operation active in a system, all these hot plug operations were being done sequentially, and on a approximately 2,000 CPU system, it was taking around 25 minutes to finish the entire.
So what was it for running?
No. So we were not running anything actually. Yeah. So even if you don't run anything, it takes around 25 minutes to finish. Not because of stock machine. It's not because of stock machine. So we tried to debug this, and we tried to figure out what time, where this most of the time is being spent. And so majority of the time was spent doing synchronized RCU. We'll talk about it in the experiments. So the takeaway from this slide will be that if you are trying to do multiple hot plug operations on a big system. So for example, if you are trying to do it on a small laptop 32 CPU system, it will be faster. I mean, it will finish in 1 or 2 seconds. Even though, I mean, one CPU hot plug operation finishes very fast, but if you line them up one after the other, then it adds up. So one more point I would want to add here, because I'm going to reference it later, which is, so for example, in case of scheduler, scheduler will do other things also. So for example, when a CPU is going away, it might need to rebuild the topology that it maintains of the system. And on a large system, building the topology is an expensive, costly task. So on a large system, what happens is when I'm doing the first CPU hot plug operation, that CPU hot plug operation will take more time than on a smaller system where I need to just build a topology of eight CPUs. Okay, so can we move to the next slide? Okay, so I wanted to talk about parallel CPU, and recently, I mean, in past 2 years, a new enhancement had been made to the CPU hot plug infra, which is parallel CPU bring up. So this patch series does not parallelize the entire, does not enable us to start running multiple hot plug operations in parallel. What it does is it parallelizes a very niche part of the bringing a new CPU or removing a CPU from a system. So this is it parallelizes one very small section in during boot up. So when I want to boot all my secondary CPUs, uh, um, yeah, I'll talk about what it parallels. So the thing what I want to mention here is that this was the first attempt to that has been made so far to implement any kind of parallelism in CPU hotplug. Uh, this improves boot up time on bare metal system. It's something while I was working to enable this series for PowerPC, we didn't see any improvement in case of PowerPC because it's mostly a virtualized platform, and this particular patch series does not show any improvement in virtualized environments. And okay. Okay, so I'll add just one more point. So the task of moving from an unordered way of invoking this callback to implementing a state machine brought us one step forward to parallelizing the CPU hotplug operation. So that state machine can now be extended, but there are some intricacies that needs to be taken care of, so it brings us one step closer. Is what I would like to uh, move away. Okay, so I'll talk about what actually was the key idea behind parallel CPU bring up, and I was thinking about how to explain it. So you can think of it like I need to pick up 5 of my friends, and the only constraint is I can pick one person at a time. So I go to my friend's place, I ring a bell, and I wait for that person to come out of the house, and only then I can go and pick other person. So in this batch series, what happens is I will go and call everybody, and I will ask everybody to wait outside. And then once I have called everybody, I'll come back and release everybody so that they can go and finish bringing themselves up. So that was the crux of this batch series. Can we move to the next step? Yeah. So this slide is also about the same thing. Previously, what we used to do is we had a mask of CPUs that we wanted to bring online. So this is during the boot up, first of all. And CPU hotplug bring up mask is a API that the CPU hotplug infra has, which will what it will do is it will go and bring each CPU one by one to the target online state. But with the new advancement which is parallel CPU bring up, what we do is we first bring all the CPUs to the state to the hotplug BPK KP, which is the state where the control CPU will start the secondary CPUs. So all of the CPUs are brought to this state, and then the control CPU will one by one bring them to the online or release them so that they can bring themselves up till the CPU online. So right now, this is what it is. So okay, one more thing that the parallel CPU bring up added was it added the concept of so it formalized the aliveness of a CPU. So when a CPU is brought, when I'm trying to bring up a CPU, so CPU itself will have a state. For example, earlier it was not executing, and now it is ready to execute. So this parallel CPU bring up series also added that infra, which can be used to run a fully parallel CPU hotplug operation. So what I mean by that is, if I want to offline 2 CPUs, those two CPUs can offline themselves without impacting other things that are happening in the system. Yeah. So can we go to second slide? Yeah, this one. So okay. So there have been other approaches, and where they try to reduce the time to finish a single CPU hotplug operation, which is identify, go through this all the callbacks, figure out which ones are taking more time, and then see if something can be done. So when we are doing multiple hotplug operations, so what happens is there would be some operation that will be executed every single time, But because we are going to immediately we are going to do another CPU hotplug operation, same operation will be executed again, and the artifact that was generated previously is now no longer needed. And one such example which was identified was in a VM stack subsystem. I mean, so can we move to the next slide? So just, taken this slide from another slide. So here, what the authors figured out was that this refresh zone stat threshold function was being executed multiple times. And because we at the boot time, if we are trying to bring 2000 CPUs, it will be executed every single time. So why can't we just do it in the end? So they came up with some infra to defer it at the end of the at the end of the boot up, so that it only gets invoked once. And then once the system is up and running later on, if somebody performs CPU hotplug, can we it will be executed every single time. Okay, so can we move to the next slide now? Yeah, so here I want to talk about all the experiments that we did. So once we hit the issue where bulk CPU hotplug was taking a lot of time, we wanted to figure out where the most of the time was being spent, and to do that we kind of took help of this off CPU time scripts that are part of the BCC and BPF trace. And while we initiate a system bulk CPU hotplug operation, through this CPU time analysis, we were able to figure out the threads that are involved in the CPU hotplug operation were sleeping for 5 seconds, and then we got the stack trace actually, and through that stack trace we found out that each stack trace was taking around 5 seconds, and then once we figured out that it was a synchronized RCU which was taking more time, in Linux kernel there is a way where we can make these synchronized RCUs expedited, which would means that the thread that executed synchronized RCU will now not wait for the grace period to finish, and it will immediately it will send ITS to all the CPUs, and it will come out of the synchronized RCU immediately. So enabling system-wide synchronized RCU expedited. What we found out that on a system which has 400 CPUs, an operation which is a SMT switch operation. So if we are switching SMT states from SMT A to SMT off, earlier if it was taking 1 minute 33 seconds, the time went down to 4.3 seconds. So which is like a 95% reduction. I would recommend people to check out this analysis which was posted by one of my colleagues upstream, where we have demonstrated we have done some more experiments. For example, if we identified which synchronized RCU was causing which stack trace was causing, if we make just that stack trace expedited instead of enabling system wide, what will be the impact on the time taken to finish the bulk CPU hotplug operation? So we have done these experiments on different size of systems. For example, one experiment, the analysis is done on one system which has 128 CPUs. In that case, also what we found out was the reduction was around 95%. So in every single case, even though actual time is different, the reduction is always around 95 to 96% of the time. The way one can enable system-wide RCU expedited is using this SSS entry. And this data is from is being taken on the latest upstream, which is 6.18. Can we go to next slide? Okay.
Sorry.
Yes.
So that work is upstream.
So we have posted our analysis upstream. So the thing is, the synchronized RCU expedited was because it sends a lot of IPIs throughout the system. We don't have any response from the community saying whether using expedited is a good idea or not. So that's one thing. Yeah. So there was no response from it, but we have posted our findings. Okay. So in this slide, so this slide is also like a kind of a hack that we were thinking about. Can we find some other operations which are when we are doing multiple CPU hot plug such operations which run as a part of CPU hot plug, but then their outcome or their artifacts are destroyed and rebuilt again. So one such thing that we knew was the SCED domain, and we wanted to see how much time we can save just by doing it if we had some interface where it allowed us to run bulk CPU hot plug operations, and then it also allowed us to move certain operations to the end of the bulk CPU hot plug. So how much time could we save? So this was just a hacky thing that we did on a whim, and we found out that on a CPU with 480 CPU system, just not building these SCED domains every single time would reduce the time taken to perform the SMT switch operation from 43 seconds to 1 minute 30 seconds. So 10 seconds we say. But the question now here comes is, if we are postponing something till the end of at the last hot plug, so the SCED domain which we began with is now invalid. That puts system in an inconsistent state. So that is something. So we need to handle that. So can we move to the next slide?
So the VM fix, by the way.
Yes.
And that was the point of conversation for that, whether the intermediate state is that important enough to be valid or can it be invalid. And I found that it was actually okay to be invalid. Some statistics that nobody was actually convinced. But SCED domain is actually a clear problem.
Yes, SCED domain. So if we are able to do something in like 5 seconds, for 5 seconds, SCED domain or load balancer will not perform will not be as efficient. So it will not be able to. So there will be some skewness in the system. But the whole point, yeah, I mean, so that is a debate that is there. I don't think I am very well to talk about it or say that we should go with this approach or that. As a future work, we were looking to bring support of parallel CPU bring up on the Power Platform. Right now, being virtualized, we don't see any gains in the for the virtualized platform, but we do observe some speed up in case of our bare metal power NV system. So that would be the future work, and then can we parallelize the entire CPU operation so that we can run once the prepare section, because prepare section will be executed by the control section. So the thing is, when you say bottleneck, it comes out of like, I don't want to do like, it's a necessary thing that you must have to do, because what will happen is you can have systems where you have created CPU sets, and what happens when the last CPU of that CPU set goes away, so you need to build those things. So it is not a bottleneck. Yeah, I mean, so. Okay, so in case of, for example, in a 200,000 CPU system, that function which builds the scheduler domain, it takes around microseconds. Like, it's not like it takes 1 second or 2 seconds. It finishes up fast. It's just the time complexity of that function is not linear. I mean, if when the CPUs increase, the time complexity of that function to finish is non-linear. Yeah. Tracing, yeah, you can enable. So there are static trace points that you can enable, and those trace points, and then you can trace using FTH or cost, and timing information will be there, so we can easily figure out which step to how much time from there. Okay, can we go to the next slide now? Okay, so the challenges that are still present. Uh, okay, so I mean, because there are so many subsystems that have registered for a callback. Uh, uh, this is the last slide actually. And so there are so many number of states, and each state is subsystem. Each callback is subsystem specific, understanding what everybody is doing will be a difficult task to do, and those callbacks are itself like a black box I mentioned before for the CPU hotplug infra. And some of these callbacks are complex, and currently we have not discussed what will happen when failures occur. So when you have only one hotplug operation and a failure occur, you can roll back to the previous, either offline or online, depending upon where you started. But if you have multiple CPU hotplug operations and you are performing 10 CPU hotplug, 5 of them succeed and 5 of them fail. So what do we do then? And we should also discuss what happens when recursive failure happens. Where I was trying to online a CPU, failure happened, I wanted to roll it back, but then while I'm executing tear down callbacks, another failure happened. So that leaves CPU in a difficult spot. Thread safety of the callbacks is something that needs to be handled. So temporary workaround that I also wanted to talk about is, if you want to do a bulk CPU hotplug, enable system-wide RCU and then perform the bulk hotplug and then disable the system-wide RCU, so that for those 5 seconds of duration, we are able to finish the hotplug operation faster instead of waiting for 25 minutes. And yeah, I mean, definitely it is a workaround, and it's not a long-term solution. Long-term solution would be we would want to fix this issue. We would want to make this CPU hotplug panel. Can we go to the next slide? So okay, so these were some of the reference material that we looked at, and then next slide. This is something, and yeah, thank you.